So with this example, we're going to continue with the future value for an ordinary annuity. We have F that's equal to D. You could think of D as a deposit or a deduction times E, that's the effective rate, over R over N. So again, I like to list my variables as I read this, so we'll give it a go. You would like to make a down payment of $6,700 for a new Harley-Davidson Fat Bob motorcycle. You decide to put away $355 every month in an account paying 7.8% annual interest compounded monthly. How long will it be before the account matures to $6,700? So we would like to make a down payment of $6,700. That's our future value. That's how much we want. So you decide to go ahead and put away, deposit $355 a month, so that's D. In an account that pays 7.8% annual interest, so that's our rate. And that is compounded monthly. So the number of compounds is 12. And of course, we're trying to find how long. So we're going to be determining T, the time it will take to get $6,700 at $355 deposited every month at 7.8% compounded monthly. So the first thing we need to do is E. We always look to find E. Again, E is that rate that's taken right from our compound interest. That's 1 plus R over N to the NT power. And again, this is a rate. A rate is per 100, so we have to subtract out 1. So then E is equal to 1 plus the rate. That's 0.078. That's over the number of pay periods. That's 12. Raised it to the 12, and here's the T that we're going to be solving for, minus 1. So I'm going to plug in the 0.078 divided by 12 because I'm going to need that for right here, right? So 0.078 divided by 12. So then E is equal to 1.0065 to the 12t power minus 1. And that's as good as we can go because we don't know what t is. And of course, that's what we're looking for. So now over to our future value. Our future value, that's $6,700. That's equal to D. That's our deposit that we're going to be putting away every month. That's $355. And we multiply that to E, which is this. So that's 1.0065 raised to the 12t power minus 1. See how that's our future value? That's equal to D times E. And then we'll divide all of this by R over N. That's this right here. That's this right here. And that's our 0.0065. Now we'll use algebra. We're going to be looking to isolate this term here because we want to isolate our variable up here. So I'll multiply both sides by 0.0065. Do it over here. These will cancel. 0.0065 times the $6,700. So that gives us 43.55. That's equal to 355. That's our deposit. Times our effective rate of 1.0065 to the 12t power minus 1. I continue with the algebra. I'll divide both sides by 355. That'll cancel and that'll cancel. 4355. I'm just going to go ahead and do the operator, divide by 355. So that's 0.1226 7606. That's equal to the 1.0065 to the 12t power minus 1. We continue with the algebra, add 1 here, add 1 on the other side. We have 1.12267606. That's equal to our 1.0065 to the 12t power. So now since we have an unknown exponent up here, we're going to need logarithms. So this will be the log of 1.12267606. That's going to be equal to the log of 1.0065 to the 12t power. Power property of logarithms says that now this side can be rewritten. So it can be rewritten as 12t times the log of 1.0065. Of course, this side is also the log of 1.12267606. Now solving for t here, divide both sides by 12 times the log of 1.0065. We do it on this side. 12 times the log of 1.0065. The 12s will cancel, the logarithms will cancel, leaving us with t. So that's going to be approximately equal to, now I'm going to enter this in my calculator, but keep in mind that I want to be able to delineate between the numerator up here and the denominator. So I'll go ahead and I'll put in my numerator here. That's the log. Here's my log key of 1.12267606. Then I'm going to divide that, but I'm going to put in this parenthesis right here. Then type in 12 times the log 1.0065, close off the logarithm, and then I'm going to close off with this parenthesis here. And hit enter. So it comes out to be 1.488344414. So the time it's going to take, t is going to be approximately equal to 1.49 years. However, keep in mind that the interest here is compounded monthly. 0.49 of a year, that's less than 6 months. That's like 5 months and 25 days. So the interest will not be paid on that last month yet. So at 1.5 years, 1 year and 6 months, it'll be paid, but not at 1.49. For mathematical reasons, we can leave our answer like this. That's fine. But in practicality, you would have to wait until the 1.5 years, the 1 year, 6 months, before you're going to get your $6,700. Actually, you're not going to get exactly $6,700 because by the end of that 6th month, you'll receive an interest payment again, so you'll actually come up with more than $6,700. But there you go.